Section 5.5, our last section for trig this semester. It's the last section in the book as well. We don't usually get through, a whole book in any math class. That's not typical. This is a skinny book if you've seen the actual book itself, but it is kind of a skinny book. But we've covered almost all the sections. We've skipped a couple here and there, but not much. We're looking at parametric equations in this one. And let me give you first the definition, and then I want to intuitively build in you the idea that you do this and think about this way all the time and you aren't aware of it. So, a plane curve in parametric equations. So suppose that t is a number in the interval I. A plane curve is a set of ordered pairs where x is equal to f of t and y is equal to g of t for an interval. The variable t is called a parameter. And the equations x equals f of t and y equals g of t are called parametric equations for the curve. All right, you guys are going to have to help me out because the example I want to use is going to depend on who's here today. Tell me what sports we play. I know football. What else do we play? And I know volleyball. Nobody's going to talk. Everybody in here plays a sport. Tell me what you play. Soccer. Basketball. Shot put. Okay. Did that get everybody? Do you have any cheerleaders in here? Yeah, and we have cheer, okay. Cheer might be the one exception to the example I'm going to give, but that's okay. Okay, so everybody else except for cheer gave me an example where you have an object, most of you it's a ball, that moves around some sort of a playing field over the course of the game, correct? Yeah, does that make sense? Okay, so at any given point in time, the ball, or in case yours is a shot put, but we'll say ball for the majority of it, the ball is at some location somewhere on the field. Or on the court or whatever, right? Everybody with me? Okay. So that location is an XY ordered pair. So imagine whatever your field is that you're looking at. The basketball court, the football field, the volleyball court, the soccer field. Imagine it. You can picture what it looks like. You've been on it forever, right? You guys have not just started playing this year. It doesn't work like that at this point, right? You've been playing forever. I know. You can picture that field. And you can sort of picture it on an XY coordinate grid, right? You can sort of put like a corner and say that there's a corner on the corner of your field. I'm going to use field because otherwise I have to keep saying words that are interchangeable. So we're going to say field and we're going to say ball, okay? So if you put a corner on there, you could use a grid to tell where the ball is at any given point. Does that make sense? Okay, so that grid is the XY, this X of t, Y of t business here, and the t is the time since the game started. So the ball moves around the field, right? But it doesn't do it like, it's not like it's because the x is affecting y. It's because it's all being affected by the time that's in the game. Does that make sense? Your location on Earth is the same way, right? It's 9 a.m. on Wednesday morning. You're supposed to be in this classroom. This is where those of you who are here are, right? This is an XY coordinate grid, if you think about the Earth laid out kind of like in a map kind of point of view, right? Because of the time, this is your location. But if we're looking at an hour from now, your location is going to change. Not because, the latitude and the longitude are changing for you in some sort of a specific way, but because the time changed. Are you with me? That's what parametric equations are. They're saying that the location that something is based on the time at which you're looking at it. How long has it been since whatever you're looking at having been started? Now, the operational status, how we work with them, is actually really straightforward. I think that you will like it. So if we're given two equations, what you'll notice is that these equations are not an x in terms of y or a y in terms of x. You have two equations, one for x and one for y. And if you were doing this in 3 dimensions, by the way, which we do in another one of my classes, there's a z component, right? And you can sort of picture what that would look like, especially if you're thinking sports, right? The ball is off the ground or on, it's high and low, right? Like there's a third dimension in most of your sports about where that ball is. Soccer, not quite so much. It should be on the ground most of the time. Right, Anna? It should be, yes. Okay, but in most of the other ones, there's an elevation change too that would make sense for a third component. So we're just doing 2 components. But they're all based on what's happening at this point in time. So if I know the point in time, and they give that to me t equal 1, I can find where it is in terms of x and y. How would I do that? You plug it in. That's it. You're just going to plug it in. So we're going to plug in. This one is 1 for t, and over here, 1 for t. All right, so what is 4 times 1? 4, and 7 minus 4 is 3. You got it. Over here, 6 times 1? 6. Plus 5? 11. So the location that this is referencing in an xy coordinate plane is the point 311. Make sense? Okay, yeah. All right, so let's take a look at how we graph these in general, because we just found, let me put it over here one more time. We just found one specific point, right? But like at t equal to 2, it's probably going to be at a different place, and at t equal to 3, it's at a different place, and at t equal to 4, it's at a different place. And so if you sort of imagine like your ball that's moving around the field, if you could follow where the ball went, right, the trajectory of the ball around the field, that's what we're looking at, is how do we draw a graph of where the ball went? Or if we were looking at our location in time, if you drew a graph, right, kind of like a drawing of where you go during the day, you would have these sort of movements, right? And you could do that, and that would be the graph we're looking at. So in order to graph this, you're going to select some values of t on a given interval. I'll show you an example of one. For each value of t, we're going to use the parametric equations to find the x and the y, just like we did on problem number 1. The third thing is that we're going to plot those points in order of increasing t, and we're going to connect them with a smooth curve. It doesn't have it written here. I think it'll be in the directions. We will show the direction that the point is moving by drawing arrows on our curve. That's something that will look different than in a typical graph that you're used to seeing. Okay, so let's take a look at one. Here we have x equals the square root of t, y equals t minus 1, and t is greater than or equal to 0. So this one's kind of nice because it gives us sort of a location that we're starting. If t is greater than or equal to 0, we probably should start with t equal to 0. That's kind of the starting place of this graph. So when I create my ordered pairs, I'm going to do it in a grid point perspective. So this is going to be my t value. I'm going to find my x, and I'm going to find y. And I'm going to give myself some space to work each of them out. I hope, at least. If not, I'll have to move my graph over a little bit as we go. So my first t value is going to be 0. Okay? If it doesn't give you t is greater than or equal to 0 like it did here, you probably want to start a little bit on the negative side of t and then go to the positive side of t. So maybe you start with like t equal to -2, and then -1, and then 0. So we're going to start with 0 because it told us it can't be less than 0. It's going to be greater than or equal to 0. And we're going to go from 1 to 2 to 3, and I think 4 is where I stopped. Yeah, that'll be enough. Typically 5 points is kind of a good description. If you still aren't sure of it at that point, you can always graph some more. All right, so we're going to take these these t values, and we're going to plug them into the equation. Now my x equation is a square root. So this first one will go into square root of x. So the 0 will go in square root of 0. What is the square root of 0? Well, it's 0. And then the next one, square root of 1, which would be 1, right? Now, square root of 2 is not a specific value, but for the purposes of us plotting it later, an approximation would be helpful. So if you put square root of 2 into your calculator, what is it approximately? It's 1 point something. Somebody's going to tell me. 1.4? Good enough for me. All right. The next one, square root of 3, again, does not have a closed form. It's an irrational number. But what is it approximately? 1.7, okay? And then I've got square root of 4. That one I do know, which is 2. So these are my x values. And while I've written them out kind of longhand, these are the points that are actually going to be plotting in a moment. Let's do our y values. So the y values are all t minus 1. So it's 0 minus 1, which is -1. And then I have 1 minus 1, which is 0. And then I have 2 minus 1, which is 1. And 3 minus 1, which is 2. And then 4 minus 1, which is 3. Now, I understand some of you are looking at me and you're thinking, like, why in the world did she write out 1 minus 1 and 2 minus 1 and 3 minus 1? That's fine. I wrote it out because I want you to look back in your notes later and to know what I did. That's all. But on your work, you probably don't need to show that, right? You can probably look at some of these and just do the value, right? Find the calculation, and that will be just fine. All right, so here's what we're going to do. We're going to draw this on a graph. Okay, so my values, notice what kinds of values we're looking at. These are not big values. And I even have some decimals that are 1.4 and 1.7, right? So when I'm thinking about drawing my graph, they need to represent the kinds of values I'm going to be graphing. So I don't need to go from negative 10 to 10 and negative 10 to 10. Shake your head if that makes sense. Okay? What's the biggest values I have? 3? Right? So I'm going to go from negative 3 to 3. I'm going to make my grid kind of big. Like I'm going to make it as spread out as I sort of reasonably can on my screen so that I have space in between to mark those fractions. Well, decimals is how I did them when I get there. And we want it to look, reasonably evenly distributed. Okay, so my grid is sort of thick, right? I've got lots of space in it so that I can graph these. Okay, so the first thing I'm going to graph is the first ordered pair. So it's x equals 0 and y equal negative 1. Let me shift this over here and make it a little bit smaller. And I'm going to do this so that we remind ourselves what we're doing. I'm taking these as ordered pairs. This is the point 0, negative 1, and I'm going to put it on the graph. So 0, negative 1 would be right here. I'll do them in yellow. Is that okay? All right. So the next ordered pair that we see is actually 1 and then 0. Okay. Well, 1 and 0 is right here. And then we have 1.4 and 1. So I need to go in between 1 and 2, not quite halfway, and then I need to go all the way up to 1. So it's going to look something like this. Right? It doesn't need to be perfect, right? Yours is a sketch. The next one then is also my other one. There's a decimal, and it's 1.7 and 2. So I'm going to go just a little bit further on the x-axis, a little bit closer to the 2, and go all the way up to y equals to 2. And then my last one is supposed to be 2 and 3. So at 2, I'm at 3 up here. And I'm going to connect these with a smooth curve, right? So the smooth curve will look something like this. It is not a line because the space that it takes, think about slope. If I go up 1 and right 1, I'd go from the first point to the second point, but that doesn't happen on the second one. So this will look curved. And the last thing that I mentioned a minute ago was that it needs to have arrows on it showing direction. I'll change the color just to draw your attention to it. But those directional arrows are part of the graph. This is the way the point, the object, in the case of our description, either us, as in we're moving around the campus, or our ball on the playing field is moving. There's a direction to it. Okay? Now, this is not the only way to graph this. This is one way, by plotting points, and some of them are going to tell you to plot points to do this. But there's another way to graph this as well. It's called eliminating the parameter. So we can eliminate the parameter t and then use rectangular equation to sketch the plane curve represented by the parametric equations. We're going to use arrows to show orientation of the curve corresponding to the increasing values of t. Okay, so we're using the exact same question. Do you see that? Y'all saw? Good. Okay, because I want you to see how it feels differently, but it's going to give us the same graph when we're done. All right? So eliminating the parameter means that I want to take those two equations, x and y, and I want to solve one of them, whichever one's easiest usually, for t. So which equation, in this case, we can probably pick. You choose. Which equation would you like to solve for t, x or y? Y. Okay, so if we take equation y and we solve it for t, what will I get? What is t going to equal from that equation? Okay, it's still going to have a y in it. Yeah, so it should be y plus 1, right? I'll add the 1 to both sides. I will have t is equal to y plus 1. Is that okay? Okay, so that's step 101. I'm going to solve for one of them. And then I'm going to take that value and I'm going to put it into the other equation for t. I'm replacing. This substitution, you've done this in an algebra course. Not for this purpose, but you've done substitution in algebra. So in place of the t, I'm now going to have y plus 1. Okay, is that all right? Now, that equation is not in a particularly friendly form, but it is a rectangular equation. Rectangular equations for us are usually better seen when we can write them as y equals. So we're going to manipulate this and solve it for y. So what would I do first? I don't take the square root, but the reverse of that. Square it. Yeah, I want to get rid of the square root. So I cannot take the square root of each of the individual pieces because if I did, I will break this apart and I can't do that with addition. If it were multiplication, I could. So we'll square the square root to eliminate it. And that will give me x squared on the left. What will I get on the right? Yep, y plus 1. Then what will I do? I will subtract 1. And in doing so, I will end up getting that this is y equals x squared minus 1. Okay, this is the corresponding rectangular equation that's solved now for y. But I think you know what this is a graph for. What is this a graph for? Okay, it's bigger than that though. It's a parabola. How is this parabola opening? Up or down? It opens up because the value in front of x squared is understood to be positive. You don't see anything there. What does this negative 1 at the end do to the parabola? Shifts it down 1. So this is the parabola, and I know it's going to look a little different than I drew before, but this would be the parabola that this is representing. Why am I getting a broader picture here than I did over here? This looks like half a parabola. Why is this one half a parabola, but this one I drew in as a whole parabola? There's something on the screen that tells you, like it is written out for you. Yep, t is greater than or equal to 0. So over here, we literally started with t equal to 0 to sort of make sure we followed that constraint, correct? We haven't paid attention to it one bit over here, and we need to now. What does the t greater than or equal 0 to tell you? Well, if you take a look down here and follow through what's happened, it tells you that this right here, where I'm replacing things, I was only supposed to get x values that were positive, because this is a positive square root, right? It doesn't have a plus or minus in front of it. Weird things happen when you square stuff. When you square stuff, you lose signs. Did you know that? Think about it. 2 squared and negative 2 squared are the exact same thing. When you square things, you lose the sign, don't you? That's what happened here. I squared this and I lost the sign. I lost in the middle of doing this the fact that my x value is supposed to be a positive number. How do I know it's positive? Because it says square root of t. And it's a positive square root. I shouldn't be getting the left-hand side of this graph. This part shouldn't be here. So my graph needs to start and have only positive values here. And we know that as the values went up, the same thing happened. My t values increased, my x values increased, my y values increased, and my direction of my curve goes like this. So it's a different perspective, but the graph is the same as it was before. Now this one has less detail on it. I didn't draw in as much detail. I just went off of our prior knowledge of what we know. We could definitely go back in and we could put some points and plot some things very specifically. In particular, this is at -1 and this is at +1 here. And then over here at 2, we're up here at 4. Something like that. Not 4, it was 3, wasn't it? I'm sorry. 3. There we go. So it look like that. Okay, So we're going to do one more. The one more we're going to do has the same directions as this because I wanted you to see another version of it. But it has a little bit of a trick, and so let me show you. So the directions are the same. I didn't write them on the same slide because do you see how much of the slide it took up just to write those directions? We need more space on this slide to work. So the directions are the same, but we're not going to write them again. So this equation is x equals 3 sine t, y equals 3 cosine of t, and the t goes from 0 to 2 pi. Now, it told me I'm supposed to eliminate the parameter. This time the parameter t is harder to eliminate. What would I have to do if I actually solved one of these equations for t? Let's talk specifically. If I wanted to take the first equation and solve it for t, what would I have to do? The 3 would move, and then what? How would I get the t out from inside of? I'd need inverse signs. And that's really messy because I'd be taking an inverse sign and stuffing it inside of a cosine. Now, we did that before, and you didn't like it. We created these triangles. They were arc trig functions. Y'all remember that? Yeah, I don't think it was anybody's favorite thing to do this semester. It's tricky. There's a lot easier way to solve this one than to solve this for the t that's happening there. So here's what so you're not going to understand why I'm doing what I'm doing, but just bear with me and follow along, and it'll become very clear. Are you with me? You're okay with that, right? We're okay with being a little uncomfortable for a moment? Okay. I would like for us to square each of these. What is x squared? Okay, so it'll be a 9, and then what? 9 sine squared of t. Everybody good with that? I know it doesn't make any sense why I did it, but is everybody okay with it? All right, cool. What if we square y? What do we get? Okay, everybody good? All right. So this is a trick. What happens now if I add x squared plus y squared together? Well, x squared is 9 sine squared of t, and y squared is 9 cosine squared of t. Why would I want to do that? Okay, so what trig identity is happening here? Do you guys see it? A Pythagorean one, right? So I will take care to pull the 9 out to make sure everybody can see it. They both have a 9 in them. I can rewrite this as sine squared plus cosine squared. Okay, the left-hand side is x squared and y squared, and I'm happy to have the x squared and the y squared there. There's nothing wrong with an x and a y being there. So this is x squared plus y squared. And sine squared plus cosine squared is 1. So my equation in rectangular form becomes this. Do you recognize what that is an equation of? We've not talked significantly about this year, but it is an algebra topic you've seen before, and geometry. You saw it in geometry too. Nope, it's not an exponential. This is a circle. It is a circle centered at 0, 0, with radius what? Do you remember? What would be the radius of this circle? 3. Radius 3. So the general form of a circle, I'll write in the general form, is actually x minus h squared plus y minus k squared equals r squared. Now we don't have anything that has these, like we don't have a minus h and a minus k. That's why it's 0, 0. The center here would be hk, and the radius is r. So it's the other side, the r squared. So the radius is r. So we could draw this, right? What am I drawing? A circle centered at the origin of radius 3. And I get to cheat a little bit because I have tools that draw nice circles. But it looks something like this. We would like to make sure that we at least label that this is over here at 3. -3 and so forth. Okay, there is one thing we still have to do. What is it? What's this graph missing? We eliminated the parameter. We did that part. Here's the directions. Go back to the directions because I don't have them on my screen. Use arrows to show direction. Right? We're going to use arrows to show direction. Now we were able to get this last one kind of for free because we did this problem twice. We knew the way the arrows were going to go, right? So we don't have that to sort of fall back on in this previous problem. So what we can do is we can actually take a look at graphing, not graphing, but the ordered pairs, I guess, if you will, for a couple of points, and we'll be able to figure out the direction. This is either counterclockwise or clockwise, right? I mean, like my arrows have to either go around the circle counterclockwise or they have to go around the circle clockwise. Are you with me? We just need to figure out which one it is. So if I take 2 points that are really nice to work with, I should be able to figure this out pretty quickly. For example, I'm going to choose 0 because 0 is always nice to work, well, not always, but it's generally nice to work with. And in terms of this being trig, a nice value would be something that I know from a unit circle going back up to the very beginning of the question, right? What's a really nice t value that I could plug in here? Somebody give me one. Think unit circle. Pi over 4 would be fine. You could do pi over 2 if you want to. Something that you don't want to go all the way over to pi because then you don't know if you got there from the top half or from the bottom half, right? We need to do something on this top half of the circle in terms of the angle measure for it to make sense and figure out if we moved upwards in the circle or if we moved downwards. So I'm going to choose pi over 2. But if you want to choose pi over 4, that would be just fine as well. And I need to know what is my x and what is my y. So if I put in 0 back into the original equation, I would have sine of 0. What is the sine of 0? It is 0, yes. And if I put 0 into the y value, which is 3 cosine of t, right? What is the cosine value at 0? That one's 1, and then it's multiplied by the 3 in front. So if I plug those in, I get 0, 3, and that should make sense because, oh wait, yeah, no, that's fine. So that should make sense, 0 and 3. And where is 0 and 3 on this picture? It's actually at the top, right? The first point that I just found was at the top of my circle. That's okay. I can start at the top of my circle with that t value. I could still go clockwise or counterclockwise. So that doesn't give me a lot of information. It just gives me the starting point. The next value is going to tell me what I need to know. So let's put in pi halves. Now we're putting pi halves in over here. So if I have sine of pi over 2, what is the sine of pi over 2? Well, it'll be 1 and then multiplied by my 3, so it'll be 3. Simon, you're right. So I've got a 3 on this one. Did everybody get that? Okay, and then what do we do for pi over 2 for cosine? What is the cosine of pi over 2? That is 0. And then times my 3 would be 0. So the first point that I just found is up here. Where did I find my second point to be? To the right. This was the second point that I just got when I put those in. So how am I going to draw my arrows? Clockwise or counterclockwise? They're going to go clockwise on this one. So my arrows are going to go around my circle clockwise on this particular problem. And I just have to test 2 points to see what happens. And I really have to have 2. If you want to confirm it and do a third one, you certainly could. But 2 is enough because it'll take me from one point to the next and give me the direction I need. All right, what do you think? A lot of it's just evaluation of functions, stuff that we've been doing, but with trig. This one had trig in it. They're not all going to have trig in it. Some of them are going to have just algebra types of equations with them as well. Okay? All right, that's it for today.